So for the first chapter, we are going to study the semigroups of linear operators. So to introduce the topic, it's interesting to come back to the single linear equation. So when you look for a function and you look for a function such that when you take the derivative, it's a real number a times the function. So the very classic, the simplest linear differential equation. And as you know, the solution of this equation is x of t equals x at time 0 times exponential of a times t. Now, what's interesting to remark with respect to this course is that you can check that this solution satisfies x of t plus s equals exponential of a times s times exponential of a times t times x0. So this comes from the property of the exponential, right? So here, this comes from the fact that x of a t plus s equals exponential of a t times exponential of as. Right? And also, if you look at x of, so now if you call it st equals of x equals exponential atx, this x here is not the best notation because yeah, here it's the initial condition, so I don't know. Okay, but whatever. So if you take s0 of x, it's equal to exponential a times 0 times x equals x. So s of 0 is the identity, right? So well, now the main purpose, the main goal of this course is to generalize these things when you're not dealing with A, but with a linear operator in a Banach space. But the idea is really that's a common thing in science. You start with simple things, simple concrete things, and then you generalize. And the theory of semigroups, which is quite complicated, so you need some theory, you need to do real abstract math, but the idea is to generalize this simple equation. So we're moving on with the uniformly continuous semigroups and the definition of semigroups. So the basic setting is that you have a Banach space X, and on this space X, you consider the set of all linear and bounded operators from X to X. So you put on X the operator norm. So there are several ways, as you know, to define the operator norm, but it's this object here. So this is the norm that you put on X. So it's known that L of X with this norm is a Banach space. Now, that's the definition, which is the title of the course. So it's an important definition. You should know it. So a family S of T, so indexed by T for non-negative T, we say that it's a semigroup of linear operators on X, or simply semigroup if. So here the definition is exactly the two properties that I have mentioned for the solution of x prime equals ax. So S at time 0, it's the identity, and S of t plus S equals S of t applied to S of S. So this is the definition of a semigroup. Now, if in addition you have that S of t converges to identity in the operator norm as t goes towards 0, then the semigroup is called uniformly continuous. So the first example of semigroups is actually so one who comes for the ordinary differential equations. That is, you will define S of t as the exponential of the matrix T times A, where A is a finite dimensional matrix n times n. All right, so what's the definition? So it's now we're going to study that on detail. So I propose you the following exercise. First, so this is the definition of the exponential of a matrix. So this is always defined. So exponential of TA is defined by this infinite sum, this series. And so the exercise is to prove that first, S of t is a uniformly continuous semigroup of linear operators, and two, that you can derive it, and in fact it's of class C1, meaning that you can derive it, and then the derivative that you obtain is actually continuous from 0 plus infinity into x. All right. So now, so to prove that that's a semigroup, first we need to prove that exponential of t plus sa equals exponential of ta times exponential sa, and this is a classical computation that follows from the series, the definition of the exponential. So you can find it in any textbook in complex number, for example, in the book of Redden. And by also the series, you have that S at 0 for t equals 0 is the identity. So now we are going to prove that the semigroup is actually uniformly continuous. And to do that, so we are considering, so S of t here minus identity, and here this is the norm. This is the norm of the operator norm. All right. So by definition, you have that S of t is defined as this series. So if you take out the identity, it's equivalent to start at 1. Now, so you can put the norm here, and here it's exactly the definition of exponential of the norm of 80. All right. So this works. Why? Why does it work so well? It's because the norm of a matrix is always finite. So so that works, and you got that, and now you're working with real numbers, and you know that exponential of 80 converges to 1 as t goes to 0, and this gives the result. All right, so we are now going to prove that we can derivate st with respect to the variable t. So to do so, we consider the expression s of t plus h minus s of t. And so if I do the computation, I just apply the definition with the series, and then I use the formula of Newton, and now what I'm going to do here is to look at the case I equals 0 specifically, right? So I split, in fact, this sum over I into, I put first I equals 0 and then the other terms. So if I do that, I obtain for I equals 0 here, I obtain that. So in fact, I obtain the same thing as here. So what? So this cancels. So now this term cancels with this term, and I obtain this quantity, which is written here. All right. And now I will divide it by h and see if this quantity converges when h converges to 0. So since I have powers of h, a lot of terms will go to 0. In fact, all of the terms, all but the one which has the power 0 in h. So let's do that. So when I divide by h, you can remark here, I have now -1 instead of I, because I divided by h. And so since h is going to converge to 0, all the terms are going to cancel, all the terms but the one for I equals 1. So only this term remains, and that's it, because now for I equals 1, I obtain exactly this quantity, but k divided by factorial k is 1 divided by k minus 1 factorial. I put the 1a in front, and I obtain exactly a exponential the 80. So what did we prove? We proved that exactly s of t, or exponential of 80, we can derivate it, and its derivative equals a exponential of 80. So which is the same thing to say that so exponential of 80 is a solution of a differential equation. All right, next we want to prove that in fact a exponential of 80 is continuous, so that s of t is of class C1. And to do so, again, I look at this quantity. So this is in the operator norm. This one was missing, so I can put now. I have all the things to do this computation, so I can put a exponential to 80 in front, and it remains that. But this one I know from the beginning. This is the first computation almost the first computation that we did. I know that exponential of AH is converging to identity in the operator norm. And so we're done. We're done. This is going to 0. So we have proven that S of t is of class C1 and that it's the derivative of exponential of 80 is a times exponential of 80. So next we have the following exercise. So you consider a Banach the Banach space of all bounded and uniformly continuous functions from R from positive time to R, and with the norm, the infinity norm. And so you define you define st of f of s by f of t plus s. So this is the left translation of t, right? And so to prove that S is a semigroup, actually, this comes from the it's come from the definition. If we replace t by 0, you have f s0 of f of s is f of s, and also s t plus w of f is s of t applied to SW of f. This comes immediately from the definition. So next, to prove that that the S is not uniformly continuous, you can consider this sequence of function, and then you will find that when you look at if you look at the strip of fn of t plus s minus fn of s, then if you look at whatever the t is, you can always find an n. So for all t, you can always find an n such that fn of and s such that fn of t plus s minus fn of s equals 1, because so this function here, if I trace here like that, then okay, yeah, so now you have a t, let's say you have a t here. And so if your 1 over n and 2 divided by n are small enough, then you if you take a f of, if you take s less than 1 over n, you have s here, and you have s plus t here, and the difference between the two is 1. So yeah, because this function is like that. So get that, and this is the function. All right.